Thanks. Yeah, first I would like to thank the organizer for this really wonderful workshop. So yeah, although we cannot come to US, but I think yeah, on Zoom we can get together and exchange interesting idea. Yeah, so I would like to also thank my postdoc, Wenyuan Liu, my student Yubin Li, and also collaborator Shou Gong, Wei Changcheng, and Didier here for this work. So yeah, we already have one work posted on arXiv, and there will also be a coming work. So yeah, so this deconfined quantum critical point is a very old topic, especially yeah, for the people who believe it might hold this key mechanism for high TC couplets. Yeah, but for this electronic material, the existence of DQCP it's still not quite clear. Yeah, but in this spin models, actually, yeah, we have a concrete example. So yeah, here, let me just briefly review this theoretical part. So theoretically, yeah, proposed by Santu and his collaborator that this so-called deconfined quantum critical point can be described by this so-called CP1 model. And in this CP1 model, if we study this square lattice antiferromagnetic magnets, the key point is that this yeah, this so-called multiple or instant events actually always change by 4, so it becomes a dangerous irrelevant operator. So this theory can describe this very interesting direct phase transition between the antiferromagnetic order and the valence bound solid order. So later, I think Anders find his very famous JQ model. So this model includes the nearest neighbor spin interaction and also this ring exchange term. So it's a involve 4 spin. So yeah, if Q is large, then it becomes this plaquet order. And if Q is small, still it's the antiferromagnetic order. And yeah, so far people can do pretty big size numerics yeah, by using quantum and color. And indeed find very strong evidence for the presence of deconfined quantum critical point. Yeah, also this deconfined quantum critical point also exists in other models. So I think yeah, yesterday's talk, yeah, people also mentioned some of these new models and a possible experimental realization. But the interesting question is that yeah, so far most of these calculations, especially for bigger system size, just tested this so-called unfrustrated model. Yeah, like this JQ model, there's no sign problem. So yeah, it looks like this DQCP phenomena is pretty general in this model. Of course, you can also go to SUN, you can go to a lot of different lattice sites, and yeah, you will observe this DQCP. But our understanding for this so-called frustrated magnets, yeah, so far still very limited, yeah, because we don't have very powerful numerics like quantum and color. So yeah, so the simplest example, many people already mentioned it, I think yesterday, and yeah, basically this so-called J1, J2 antiferromagnetic model. So yeah, on the square lattice, if J1 is very big, then it's the usual antiferromagnetic ordered phase. If J2 is very big, it's the collinear phase. And if you're doing this mean field calculation, you will find that you just have this first order transition at J2 over J1 equal to 0.5. So yeah. So now the puzzle is that although people believe that yeah, if we include quantum fluctuation, this classical phase diagram is not valid, and there must be some paramagnetic phase yeah, around this 0.5. But now I think the debate is that it's could be a DQCP just from this AFM order to the VBS order, or it can be a stable so-called quantum spin liquid phase. So yeah, actually, yeah, people have this puzzle for almost more than 20 years. So yeah, some early DMRG calculation actually shows very exciting evidence for this presence of the so-called gapped quantum spin liquid. So this is a DMRG calculation. People show that this both spin triplet gap and the spin singlet gap now vanish in this intermediate region. So basically from J2 over J1 around 0.45 to 0.62, I think in all these regions, pretty, it shows that there's no any magnetic order. And of course here, after 0.61, people believe just the first order transition. So the physics pretty simple. So the most puzzle region is just in this region between this 0.45 to 0.6. Okay, so then some later DMRG calculation with AC2 symmetry. So the effective states people can keep effectively can much bigger than the calculation without AC2 symmetry. So there people find a very different story. Actually, the most intermediate area become this so-called plaque BBS order. Of course, there are still could be a very small gapless region, and also confirmed by very recent excited states calculation, and the region could be slightly extended to 0.52. But most of this paramagnetic phase is still a plaque BBS. But we also we know that DMRG is essentially still a quasi 1D system, so we can gain some understanding for the 2D system, but the real 2D limits may be still very different. So also there are some other 2D variation approach, like this so-called string boson approach, and Salil boson approach. So the string boson approach basically the best variational state is so-called short-range RBB state. That's first proposed by Phil Anderson. And it turns out around the 0.5, the variational energy also very good. If we compare with the exact diagonalization, it's almost within 1% accuracy. But this Salil boson variational Monte Carlo approach shows even promising results. So there's a so-called Z2 gapless spin liquid. So this gapless spin liquid has a couple to has this so-called Dirac fermion coupled to the Z2 gauge field. So at low energy, this Z2 gauge field just gap out. So the major low energy contribution from the Dirac fermion. So we will expect 1 over R quartic decay for the spin correlation at a long distance. So for the short-range RBB state, just exponential decay. But these two features looks like quite different from the numerical results from DMRG, because in DMRG people claim in this most region it's a plaque BBS just because the spin correlation actually decay exponentially. So this is actually quite a puzzle if we compare this 2D and 1D results. But of course, the 2D results we can say it's biased because just the variational ansatz. But energetically, actually, it's still pretty good. So of course, yes. So for this workshop, we are looking for a much unbiased method, and I think Frank already gave a pretty detailed introduction for what is so-called projected entanglement paired states. Sometimes we also call the tensor product states or tensor network states. So the basic idea is that we can just generalize this so-called MPS algorithm into high dimensions. So matrix product state is equivalent to this DMRG. And in high dimension, like in this cartoon, we have M1, M2, M3, M4 represent physical degree freedom. So for each spin up or spin down configuration, we just have two different tensor. So if we consider a uniform state, we can put all the tensor to be the same. But in realistic calculation, especially for finite size calculation, we also prefer all the tensor to be different, such that we can capture better for the boundary states. So of course, in this case, the variational space, the variational the total variation variable, the unknowns becomes much bigger, and it could cost much long computational time to get the ground state energy. Okay, so for the algorithm, I briefly mentioned this idea because the time limit. So basically, it's a very standard this MPS algorithm apply on open boundary condition, and because we have this physical states, so we need to do some so-called Monte Carlo sampling. So for each sample, we just fix the physical states, and that's also very standard, important with the sampling methods. So after we sample these physical states, so we can efficiently compute all the physical quantities like ground state energy, correlation functions. So the second point is that we also need to minimize the ground state energy. So this could be a very hard step, but the trick we use is that we start from some so-called simple updated states, or sometimes we use the improved loop update or cluster updated states. The key is that we need some good variational starting point. Then we apply this very time consuming so-called stochastic gradient optimization method. And finally, we can push a limit. We can do d equal to 10. But here just for time saving, in most cases we just compute for d equal to 8, and we will see that if the system size is not very good, actually it's if the system size is not very big, this d equal to 8 actually big enough to capture the all the properties of correlation functions. So now we can just briefly look at this benchmark for the J2 equal to 0 point. Here just the finite size scaling for the ground state energy and the magnetization. So this ground state energy, actually we choose different central bulk. So like we choose this central bulk L by equal to L, or L minus 2, L minus 4, and so on and so forth. And we see that if we do very careful finite size scaling, they all point to the same ground state energy in the infinite size limit. And it's the same thing applied for the magnetization. And all these quantities turns out to be precisely agree with the quantum Monte Carlo results. And actually, we can also have more detailed comparison with quantum Monte Carlo on each side. Just compare this ground state energy and magnetization on each system size, and we all find the systematic agreement. So that means this d equal to 8. It's actually good enough for system size. Here, the biggest system size is 32 by 32 here. You can see the size from this 1L. So for more details of the algorithm, you can just look at the paper. Okay, so the most interesting thing is that what happened for non-zero J2. So here just a comparison for the ground state energy for the most tricky point, 0.55, because in the previous study, people see that at this point, you see there are a lot of disagreement. It's 0.55. It's kind of deep inside this quantum spin liquid in the early DMRG calculation, and here it's actually already in the VBS phase. So so first thing we really want to see whether this is already in the VBS phase or it's something else. So we do similar finite size scaling for the ground state energy for the d equal to 8 ansatz, and here for this frustrated system, due to this convergence of ground state energy, the biggest size we can do just 24 by 24. But we still see the ground state energy converge pretty well. And if we compare with the DMRG ground state energy and the VKMC, even with length source projection, actually we see it's comparable with the finite size scaling of all these methods. And this DMRG results, of course, obtained from the cylinder geometry, and the VMC from PBC conditions. But if we do a very careful finite size scaling, the boundary effect actually should be not important. Next, we look at this so-called antiferromagnetic order parameters. The stagger magnetization. So here we actually measure this square of the stagger magnetization. So we indeed see that around 0.45, the stagger magnetization vanish if we do very careful finite size scaling. And we can also compute this so-called correlation length defined in this way. And we still see this boundary for this for the crossing point actually around 0.45. So the more accurate estimation shows that at the transition point actually is 0.46. So this is perfectly agree with the almost all previous DMRG results. Yes, both with SU2 or without SU2. Yeah, so the case without SU2, there's some slightly shift for the phase boundary. Here maybe, with SU2 here maybe 0.44, but it's almost surrounded this 0.45. So all the methods seems agree with each other. So now the most interesting thing is that this comparison of the correlation functions. So for this correlation function comparison, we will see this DMRG calculation. In order to capture the long-range correlation, really needed to push the limit to keep the state, even with SU2 symmetry, keep the state up to more than 10,000, such that the correlation function can match this PEPS calculation. So this 0.55 point, it's actually even harder. Even you increase this, you continue increase this states keep by DMRG, still the convergence is very slow for the correlation functions. Even this energy of DMRG always good, actually always slightly better than the PEPS calculation even with D equal to 10. But here we see this correlation functions actually always not as good as PEPS calculation in the DMRG calculation. But if we really push the limit and assume this DMRG, we can keep the state go to infinite. Actually, this boundary always consistent with PEPS calculation. So now we kind of believe that for this D equal to 8 ansatz, maybe the correlation length is enough to capture the long-range physics. For this specific system size, here we just choose 10 by 28 or 12 by 28. So here we don't choose the square geometry because we want to see these longer correlations. So more detailed calculation for this even bigger size, up to 16 or 20 by 28. We see more and more clear in all these regions for both 0.5 and 0.55. This spin-spin correlation actually decay polynomial. It's not an exponential decay. Here's a double log plot. So here is a semi-log plot. Only for this 0.458 point, it decay exponentially. We can also perform this so-called two-component fitting. Because you will see for finite size system, this decay always has an exponential component plus power law component. But if we increase the system size, we see this exponential component becomes smaller and smaller for both 0.5 and 0.55. Eventually becomes power law decay. But for the systems with J2 over J1 bigger than 0.56, actually here we see all the data shows very good exponential decay. So in this region, the system pretty looks like pretty close to a VBS phase. So in order to confirm the presence of the VBS phase, we further compute this VBS order parameter. And here just again the finite size scaling data, and we indeed see that this VBS behavior appear when J2 over J1 beyond 0.56. Yeah, so more better estimation is 0.56, not 0.57. So the intermediate phase now looks like could be a potential gapless quantum spin liquid because the spin-spin correlation is decay power law. And we can further look at this dimer-dimer correlation, and we see that in the intermediate phase, especially for these 2 points, the dimer-dimer correlation also decay in a power law. And this we can further examine the so-called horizontal dimer order parameter defined in this way. So this is just basically the energy difference of the strong and weak bond measuring from one boundary. And we see that when the system crossing this J2 over J1 equal to point, oh, sorry, yeah, this is the older figure. Yeah, actually our new figure, we will see that this 0.58 actually, we will see this superlinear behavior. So which indicated this VBS order really develop pretty fast in the bulk. Yeah, but if we compare with the so-called Schrödinger RVB states from the Schwinger boson theory, we will see the behavior in the intermediate phase actually pretty similar for this dimer-dimer correlation. So that also indicated this Schrödinger RVB phase could also be a very good metastable state for the J1, J2 model. So finally, we can further fit in this so-called universal scaling function to determine this phase boundary. So again, we find a two-phase boundary around the 0.46 and the 0.56. Yeah, so here we also see this correlation lines exponent at both transition. Actually, they are pretty close to 1, and quite different from this previous calculation in JQ model. So there are also additional evidence to show it might be very different from the DQCP scenario. Of course, this first order transition around the 0.61, it's pretty clear. And I think all the previous calculations just agree with each other. So here is a brief summary about this phase diagram. So in this very big region, we find a potential gapless quantum spin liquid phase. To further verify whether this gapless quantum stable quantum spin liquid phase is really a stable phase or just some finite size numerical effect, we also examine this so-called J1, J2, J3 model. So in this model, we added this J3 frustrated term. We can further stabilize the quantum gapless quantum spin liquid phase, especially for J2 vanish, and we will see this phase boundary from 0.3 to 0.4 becomes much sharp, and this finite size scaling data collapse also shows much better behavior. And the quantitatively results are actually very similar. If we enter this gapless quantum spin liquid region, we will see this spin-spin correlation just decay in a power law behavior. And in this VBS region, just decay exponential. Yeah, so here, this figure is just for J2 equals 0. And for non-zero J2, it basically have very similar behavior. Here is again the finite size scaling data collapse. So we will see something very interesting along both critical line. This correlation length exponents are intrinsically close to 1. Yeah, so this is intrinsically different from all the previous DQCP calculation. The new typically much smaller than 1. And you will see this for the eta S and eta D, the anomalous anomalous dimension for this spin-spin correlation and diamond-diamond correlation along this critical line, also pretty close to, all the data, they also pretty close, although have some fluctuation due to the finite size effect. But this new actually, pretty stable for all these fitting. So finally, let me just give a potential theoretical understanding for such kind of gapless spin liquid near the DQCP. So this so-called topological Sila term or Hopf term, people believe might exist in the antiferromagnetic system, especially in lower dimensions. So in 1+1D, that's a very famous very famous term proposed by Hao-Dan, and which point out the intrinsic difference between this spin, this integer and half integer spin system. But in 2D, for a long time, people believe such a term actually does not exist in the antiferromagnetic Heisenberg model. However, I think it's still not clear what happens if we go away from this AFM order region, especially in the presence of strong frustration. So if we assume such kind of term might emerge near the DQCP, then we find actually there could be a very natural explanation for the gapless quantum spin liquid. This is just because if we start from DQCP and we add this so-called topological Sila term, basically it's a transcendence term, and we can rigorously prove that the partition function of such a Lagrangian with a Sila term just exactly equivalent the four components of Dirac fermions. Basically, there are kind of four Dirac cones. And naturally, we may conjecture these Dirac cones. They are located at the momentum plus minus pi over 2 and plus minus pi over 2 in order to preserve all the lattice symmetry. And in general, if we add a Maxwell term in the system, and we will also expect interactions among all these Dirac fermions. So here, that's the final page. So basically, we compute this structure factor. So we will see, starting from J2 equals 0, still in the J1, J2 model, we see a very sharp peak at pi. If we turn on J2, here still in the AFM region, it's still very sharp. Here is almost close to the phase transition point. So in the intermediate region, this peak at pi becomes much broadened, and there's a sub-peak structure appear near this pi 0, or this pi 0, pi 0, 0 pi point. So this sub-peak behavior actually might be contributed by the scattering of Dirac spin-ons at different momentum points. So finally, there's a discussion and a potential future direction. So basically, we're applying this final PEPS algorithm with Monte Carlo sampling and the stochastic gradient optimization method. We are able to study some interesting frustrated magnets model. The most interesting thing is that we see this gapless quantum spin liquid might emerge from the underlying deconfined quantum critical point if we add a topological Sila term in the system. So this Hopf term, generally people might expect it could exist for spin 1/2 system. So that also indicates a very different behavior for integer and half integer frustrated magnets. So such kind of gapless spin liquid might never exist in integer spin system. Of course, there are also certain limitations for this finite PEPS algorithm with open boundary conditions. If we can perform PBC calculation, we should expect much beautiful results. But here we see that if we carefully doing this finite size scaling, still we see the thermodynamic limit ground energy actually are pretty good. We can have very good fitting for all the physical quantities in the thermodynamic limit. So in the future, we will still work on this PBC algorithm. But of course, it's very similar to this DMRG. So the PBC algorithm could be much harder, both for computing physical quantity and for the optimization. So hopefully we can still improve the efficiency and get a more controlled result in the near future. So finally, if we're back to this model, if we can dope this model, here we will have a prediction that this doped gapless spin liquid might be a D-wave superconductor. So this might also related to this key mechanism of the high TC cuprates. Okay, thanks.